Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video lecture, we are going to read carboxylic acids. Introduction. Organic compounds containing COOH as the functional group are called carboxylic acids. The COOH group, which itself is made up of a carbonyl group and a hydroxyl group, is called carboxyl group. Carb from carbonyl and oxyl from hydroxyl. Carbonyl plus hydroxyl is equal to carboxyl. Carboxylic acids may be aliphatic or aromatic according as the COOH group is attached to an alkyl group or a hydrogen atom or an aryl group. Their general formula are aliphatic carboxylic acid and aromatic carboxylic acid is given below, where R is equal to H or any alkyl group, where AR is any aryl group. Aliphatic or aromatic carboxylic acids are further classified as mono, di, tri and polycarboxylic acids according as they contain 1, 2, 3 or many carboxyl groups in their respective molecules. A large number of carboxylic acids are found in nature. Actually, higher members of aliphatic carboxylic acids containing 12 to 18 carbon atoms occur in natural fats as triesters of glycerol. Therefore, these are called fatty acids. Carboxylic acids serve as starting materials for preparing a number of other important compounds such as acid chlorides, anhydrides, esters, and amides. Therefore, in this unit, we will discuss in some detail the chemistry of monocarboxylic acids. Electronic structure of the carboxyl group. In the carboxyl group, the C atom is attached to the oxygen atoms, one by a double bond and the other by a single bond, which in turn is linked to a hydrogen atom by a single bond. The remaining free valency of the C atom of the carboxyl group is satisfied by a H atom or an alkyl group. Thus, the electronic structure of a carboxylic acid is where R is equal to H or any alkyl group. Electron and neutron diffraction studies have revealed that COOH group is a planar species. This suggests that the carbon atom and the two oxygen atoms are sp2 hybridized. The two sp2 hybridized orbitals of the carboxyl carbon atom overlap with one sp2 hybridized orbital of each oxygen atom, while the third sp2 hybridized orbital of carbon overlaps with either a s orbital of H atom or a sp3 hybridized orbital of C atom of the alkyl group to form these sigma bonds. Each of the two oxygen atoms and the carbon atom are left with one unhybridized p orbital which is perpendicular to the sigma bonding skeleton. Figure 5.1. Look at in the figure 5.1 skeleton delocalized pi bond of a carboxylic acid molecules. Look at this. All these three p orbitals being parallel overlap to form a pi bond which is partly delocalized between carbon and oxygen atom on one side and carbon and oxygen of the OH group on the other side. Figure 5.1b. In other words, RCOOH may be represented as a resonance hybrid of the following two canonical structures. As a result of resonance, the CO single bond length in carboxylic acids in shorter 1.36 angstrom than the normal CO single bond 1.43 angstrom in alcohols and ethers, and C double bond length in carboxylic acids in slightly longer 1.23 angstrom than normal C double bond 1.20 angstrom in aldehydes and ketones. Alcohol, carboxylic acids, aldehyde and ketone. Look at this. Comparison of resonance structures of carbonyl group and carboxyl group. As discussed in Unit 4, a carbonyl group has two resonance structures. However, for a carboxyl group, three resonance structures A, B and C can be written. A, B and C. Look at this. In both structures A and C, the C atom and the two O atoms have 8 electrons in their respective valence shells, while in structure B, C atoms has only 6 electrons. Therefore, structure B is less stable than structure C. In other words, the two important resonance structures of carboxyl group are structures A and C. In both these structures, carboxyl carbon is electrically neutral. However, in case of aldehydes and ketones, only one structure is electrical neutral. As a result, the carboxyl carbon of the resonance hybrid is less positive and hence less electrophilic than the carbonyl carbon of aldehydes and in ketones. However, it may be noted that like carbonyl group, carboxyl group is also polar due to resonance structures B and C. Nomenclature of carboxylic acids. Aliphatic acids. The aliphatic monocarboxylic acids are commonly called fatty acids because their higher members such as palmitic acid, stearic acid, oleic acid are obtained by hydrolysis of oils and fats in which they occur at the triacyl glycerides. The aliphatic monocarboxylic acids are named by the following two systems: common or tribal names. The common names of aliphatic monocarboxylic acids are derived from the Greek or Latin name of the source, plant or animal product from which they were first isolated. The irritation resulting from an ant bite is due to formic acid, Latin formica ant, which was first prepared by distillation of red ants, acetic acid, Latin actum, vinegar, butyric acid, Latin butyrium, butter, and caporic and capric acids, Latin capar goat, are some other such examples. IUPAC names. The IUPAC name of the saturated monocarboxylic acid is alkonic acid. Their names are derived by replacing the terminal E from the name of the corresponding straight chain alkane by the suffix oic acid. Alkane E plus oic acid, alkanoic acid. The common IUPAC names of some common monocarboxylic acids are given in table 5.1. Common and IUPAC name of some saturated monocarboxylic acid. Here the structural formula: common name, name of the corresponding alkane, and IUPAC name. Formic acid, methane, methanoic acid, acetic acid, ethane, ethanoic acid, propanoic acid, propane, propanoic acid, and butyric acid, butane, butanoic acid, and valeric acid, pentane, pentanoic acid, caproic acid, hexane, hexanoic acid, caprylic acid, octane or octanoic acid, capric acid, decane, decanoic acid, uric acid, dodecane, dodecanoic acid, myristic acid, tetradecane, tetradecanoic acid, palmitic acid, hexadecane, hexadecanoic acid, stearic acid, octadecane, octadecanoic acid. The substituted and branch chain acids are named as derivatives of the longest straight chain acids. The positions of the substituents are indicated by Greek letters alpha, beta, gamma, etc. with the carbon adjacent to the carboxyl groups being designated as the alpha in the common system. However, in the IUPAC system, the positions of the substituents are indicated by Arabic numerals with the carboxyl group being numbered 1 as shown below. The IUPAC names of some branch change or substituted acids are given below. The corresponding common names are given in parentheses. 3-bromo-4-phenyl pentanoic acid, 3-phenyl propanoic acid, prop-2-enoic acid, bute-2-enoic acid, 3-phenyl prop-2-enoic acid, prop-2-benoic acid, oxoethanoic acid. Aromatic acids. The simplest aromatic monocarboxylic acid is benzoic acid. The IUPAC names of the substituted acids are derived by prefixing the name of the substituent to the name of the parent acid, benzoic acid, and its position indicated by an Arabic numeral with the carbon atom carrying the COOH being numbered 1 or by the prefixes O412 or ortho 412, meta 413, and para 414. For example, benzoic acid, 2-methyl benzoic acid, 2-hydroxybenzoic acid, 2-amino-benzoic acid. Methods of formation. Some of the principal general methods of preparation of carboxylic acids are described below. From primary alcohols and aldehydes. The primary alcohols and aldehydes are readily oxidized to the corresponding carboxylic acids with common oxidizing agents such as KMNO4 in neutral, acidic or alkaline media, or by K2Cr2O7 or CrO3 in acidic medium. Oxidation with K2Cr2O7 or CrO3 in acidic media often gives some amount of esters. Therefore, oxidation with KMNO4 in neutral or alkaline medium is preferred. Under these conditions, potassium salt of the acid is first formed, which upon treatment with dilute H2SO4 gives carboxylic acids. Example, isobutyl alcohol to form isobutyric acid, benzyl alcohol to benzoic acid. Aldehydes are easily oxidized to the corresponding carboxylic acids even with mild oxidizing agents such as Tollens reagent, acetaldehyde to acetic acid. From alkyl benzenes. Aromatic acids are obtained by the oxidation of alkyl benzenes with a number of oxidizing agents such as acidic or alkaline potassium permanganate, acidified potassium dichromate, chromic acid, or even dilute HNO3. During these oxidations, the aromatic nucleus remains intact but the side chain is oxidized to a COOH group. Irrespective of the length of the chain, the COOH group formed is always attached to the aromatic ring, and the position of the COOH group indicates the position of the original side chain in the starting arene. For example, toluene or ethylbenzene or N-propylbenzene benzoic acid, p-nitrotoluene, p-nitrobenzoic acid. From nitriles. Hydrolysis of nitriles with a boiling mineral acid or an alkali yields the corresponding carboxylic acids: anitrile carboxylic acid, acetonitrile acetic acid, benzyl cyanide phenyl acetic acid, benzene nitrile, benzone nitrile, potassium benzoate. Alkyl and ara-alkyl cyanides needed for the purpose are themselves prepared from alkyl and ara-alkyl halides by treatment with KCN, with aryl cyanides are prepared from the corresponding diazonium salts by treatment with KCN in presence of CuCN. Thus, the hydrolysis of nitriles provides a useful method for the preparation of carboxylic acids containing one carbon atom more than the original alcohol or the alkyl or ara-alkyl or the array halide. Mechanism. Acid hydrolysis of nitriles occurs by the following mechanism: alkyl cyanide to carboxylic acids. Basic hydrolysis of nitriles occurs by the following mechanism: acid amide to carboxylate ion. Hydrolysis of acids, chlorides, anhydrides, esters, and amides. All these acids derivatives upon hydrolysis give the corresponding carboxylic acid. Their ease of hydrolysis, however, varies markedly and follows the order: acid chlorides, acid anhydrides, esters, amides. While acetyl chloride reacts instantly with water, acetic anhydride reacts rather slowly. Esters and amides, on the other hand, can be hydrolyzed only by heating them with either a mineral acid or an alkali. While esters are hydrolyzed easily, amides react at much slower rate. Although hydrolysis of acids, chlorides, and anhydrides is seldom used as a practical method for preparing carboxylic acids, the hydrolysis of two naturally occurring classes of acid derivatives, that is oils and fats, esters and proteins, polyamides, have been used for preparation of certain acids. Carbonation of Grignard reagents and organolithium compounds. Carboxylic acids can be prepared by the action of Grignard reagents and organolithium compounds on crushed dry ice, solid carbon dioxide suspended in ether. The addition product thus formed on decomposition with a mineral acid gives the carboxylic acids. Grignard reagent plus dry ice in the presence of dry ether, carboxylic acid. Organolithium compound plus dry ice to carboxylic acids. Sag-butyl magnesium bromide plus dry ice, 2-methyl-butanoic acid. Cyclopropyl-lithium in the presence of dry ether, cyclopropanes carboxylic acids. Phenyl lithium to benzoic acid. Both the nitrile and the Grignard reagent and organolithium compounds methods are useful for converting an allyl or aryl halide to the carboxylic acid having one carbon atom more than the present in the alkyl or the aryl halide, ascending the series. Malonic ester and acetoacetic ester syntheses. Mono and dialkyl derivatives of acetic acid can be easily prepared by malonic ester and acetoacetic ester syntheses as described below. Malonic ester synthesis. Diethyl malonate, commonly called malonic ester, is an active methylene compound. The acidic H atoms of the active methylene group can be abstracted by a strong base such as metallic sodium or sodium ethoxide to form sodium-malonic ester. Thus, upon treatment with an alkyl halide undergoes alkylation to form monoalkyl derivative of malonic ester. The monoalkyl malonic ester still has one acidic hydrogen and hence can similarly be converted into dialkyl malonic ester. Sodium ethoxide plus the diethyl malonate, sodium malonic ester, monoalkyl malonic ester, dialkyl malonic ester. The mono and dialkyl malonic esters thus formed upon hydrolysis with aqueous NaOH or KOH followed by the acidification gives the corresponding mono and dialkyl malonic acid. These acids upon subsequent heating undergo decarboxylation to form the corresponding mono and dialkyl derivatives of acetic acid. Thus, monoalkyl malonic ester, alkyl acetic acid, dialkyl malonic ester, dialkyl acetic acid. By using suitable alkyl halides, malonic ester syntheses can be used to prepare any acid. To illustrate this method, suppose we want to synthesize N-valeric acid. This may be regarded as N-propyl derivative of acetic acid. In order to synthesize these acids, sodium malonic ester should be first converted into N-propyl malonic ester by reaction with N-propyl bromide, and the N-propyl malonic ester thus obtained upon hydrolysis and subsequent decarboxylation should give the desired acid as shown below. Malonic ester, sodium malonic ester, N-propyl malonic ester, and valeric acid. Acetoacetic ester syntheses. Like malonic ester, acetoacetic ester can also be used to synthesize any mono or dialkyl derivative of acetic acid. For this purpose, the acetoacetic ester is first converted into its sodium salt by treatment with the metallic sodium or sodium ethoxide. Alkylation of sodioacetoacetic ester with an alkyl halide gives the corresponding monoalkyl acetoacetic ester. This process may be repeated to form dialkyl acetoacetic ester as shown below. Acetoacetic ester, sodioacetoacetic ester, alkyl acetoacetic ester, dialkyl acetoacetic ester. The mono and dialkyl acetoacetic esters thus obtained upon acid hydrolysis with concentrated aqueous or ethanolic KOH followed by acidification with a dilute mineral acid gives a molecule of acetic acid and a molecule of alkyl acetic acid or dialkyl acetic acid. For illustration, consider the synthesis of 2-methylbutanoic acid as described below. Acetoacetic ester, ethyl acetoacetic ester, 2-methylbutanoic acid. Hydrolysis of 1,1,1-trihalides. Carboxylic acids can also be prepared by the hydrolysis of 1,1,1-trihalides with an alkali. 1,1,1-trihaloalkane. Carboxylic acids, benzotrichloride, benzoic acid. Oxidation of methyl ketones. Methyl ketones on treatment with a solution of sodium hypohalite undergo haloform reaction to give the corresponding haloform along with sodium salts of carboxylic acids containing one carbon atom less than their respective parent ketones. The sodium salts by carboxylic acids on acidification gives the corresponding acids. For example, pentane to on sodium butanoate iodoform, butanoic acid. Baeyer-Villiger oxidation. Baeyer-Villiger oxidation of ketones with para acids per acids gives esters, which upon hydrolysis gives the corresponding carboxylic acids. Ketone plus per benzoic acid to form ester. Ester to carboxylic acids. Ardent estered homologation. The conversion of an acid into its next higher homologue is called homologation of an acid. It can be easily carried out using ardent estered synthesis. It involves the following steps: carboxylic acids, acid chloride, diazoketone. In the presence of Wolff rearrangement, a ketone, higher homologue of acid A. The acid is first converted into acid chloride by treatment with SOCl2, which is then treated with diazomethane to form a diazoketone. On treatment with Ag2O, the diazoketone undergoes Wolff rearrangement to form a ketene, which upon hydrolysis and subsequent automerization gives the higher homologue of the acid. From olefins, monocarboxylic acids may be prepared by heating an alkene with carbon monoxide and steam under pressure at 573 to 673 Kelvin. In the presence of catalysts such as H3PO4, for example, ethylene plus steam, propanoic acid, propylene plus steam, isobutyric acid. This acid at a catalyzed hydrocarboxylation of olefins is called Koch reaction. From sodium haloxide and carbon monoxide. When a suitable sodium haloxide is heated with CO under pressure, it gives sodium salt of the carboxylic acids, which upon subsequent acidification gives the corresponding acid, thus sodium haloxide, sodium carboxylate, उधर जाके carboxylic acid. Physical properties. Some important physical properties of carboxylic acids are given below. Smell. The first three aliphatic acids, formic acid, acetic acid, propanoic acid, are colorless, pungent smelling liquids. Butyric acid has odor of rancid butter. The next five acids from C5 to C9 are also colorless, oily liquids with somewhat unpleasant smell, but the acids with 10 or more carbon atoms are colorless, waxy solids with no distinct smell, probably due to low volatility. Most of the aromatic acids exist as colorless solids with no distinct smell. Solubility. Amongst the aliphatic acids, the first four acids are fairly soluble in water, while pentanoic acid and valeric acid and hexanoic acid, caproic acid are only slightly soluble. In contrast, the acids containing 7 or more carbon atoms are practically insoluble in water due to an increased proportion of the hydrocarbon part in the molecule. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water but sufficiently soluble in hot water. Since the non-polar hydrocarbon part overweights the effect of the polar COOH part, however, all carboxylic acids are soluble in less polar organic solvents such as benzene, ether, and alcohol. The solubility of the lower members in water is due to H bonding, in which carbonyl oxygen atom forms H bonds with H atoms of water and hydroxyl hydrogen forms H bonds with the oxygen atom of water as shown below. As the acids of the alkyl group increases, the solubility of the acid decreases due to an increase in the hydrocarbon part of the molecule and reduced polarity. Boiling points. The boiling points of carboxylic acids are much higher than those of hydrocarbons and somewhat higher than those of aldehydes, ketones, and even alcohols of comparable molecular masses. This means that carboxylic acids form even stronger intramolecular H bonds than alcohols. This may be explained as follows. As compared to alcohols, the OH bond in carboxylic acid is more strongly polarized due to adjacent electron withdrawing carbonyl group. Therefore, the carboxylic acids form stronger H bonds. The negatively polarized oxygen atom of the carbonyl group can also form H bonds with the positively polarized hydrogen atom of the OH bond of the other molecule. These hydrogen bonds are so strong that they are not broken even in the vapor phase. In fact, in vapor phase and in aprotic solvents, most of the carboxylic acids exist as cyclic dimers in which the two molecules of the acid are held together by two strong hydrogen bonds. Dimerization in vapor state or in aprotic solvents. The existence of such cyclic dimers is supported by the fact that the molecular mass of acetic acid in solvents like benzene, as determined by measurement of colligative properties such as depression in freezing point, is 120 instead of 60. Further, the presence of an 8-membered ring has been confirmed by electron diffraction studies in the liquid state, and in the solid state, more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding occurs. Melting points. The melting points of aliphatic carboxylic acids do not show a regular pattern. The first 10 members show oscillation or alternation effect. The melting point of an acid containing even number of carbon atoms is higher than the next lower and next higher homologous containing odd number of carbon atoms. This may be explained as follows. It has been shown by X-ray diffraction studies that acids containing even number of carbon atoms have a carboxyl and terminal methyl groups on the opposite sides of the zigzag carbon chain. As a result, they fit closely in the crystal lattice, thereby increasing intermolecular forces of attraction, resulting in higher melting points. On the other hand, carboxylic acids with odd number of carbon atoms have the carboxyl and terminal methyl groups on the same side of the zigzag carbon chain. These fit poorly in the crystal lattice and hence have lower melting points. Contains even number of C atoms, fits closely, has higher melting point. Terminal groups are on opposite sides. Contains odd number of C atoms, fits poorly, has lower melting point. Terminal groups are on the same side. The melting points of aliphatic acids having more than 10 carbon atoms do not show the oscillation effect. The melting points and boiling points of aromatic acids are usually higher than those of aliphatic acids of comparable molecular masses. This is possibly due to the reason that planar benzene ring in these acids can pack closely in the crystal lattice than zigzag structure of aliphatic acids. Acidity of carboxylic acids. Carboxylic acids are more acidic than alcohols and phenols but are much weaker acids than the mineral acids, nitric, sulfuric and hydrochloric acids and sulfonic acids. In aqueous solutions, the carboxylic acids ionize and exist in dynamic equilibrium between carboxylate ion and hydronium ion. According to law of mass action, the equilibrium constant K can be expressed as since water is taken in large excess, its concentration H2O remains constant. Therefore, the above equation can be rewritten as the new equilibrium constant K0 is called the dissociation constant of the acid. It varies only with temperature for the given acid. From the above equation, it is clear that the value of Ka is directly proportional to the concentration of H3O positive ions or simply H negative ions. Therefore, the value of Ka is a measure of the acid strength of an acid. Evidently, greater the value of Ka, greater in the tendency of the acid to ionize and hence stronger is the acid. pKa values. The numerical values of Ka of different Bronsted acids cover a range of many powers of 10. Therefore, it is sometimes more conventional to express the acid strength of an acid in terms of its pKa value, which is the negative logarithm of the equilibrium constant Ka. That is, evidently smaller the numerical value of pKa, stronger is the carboxylic acid. Thus, carboxylic acids with pKa of the order of 5 are much weaker acids than mineral acids and that of H2SO4. However, they are much stronger acids than phenols or with pKa of the order of 10 and alcohols with pKa of the order of 16. Thus, both Ka and pKa can be used to compare the acidic strength of different carboxylic acids. The and pKa values of some important aliphatic and aromatic acids are given in table 5.2. 5.2 Ka and pKa values of some acids at 298 Kelvin. Look at in this table. Structure of carboxylic acids and their acidic nature. Carboxylic acids may be regarded as a resonance hybrid of the structure 1 and 2 due to the presence of positive charge. Oxygen atom attracts the electrons of the OH bond towards itself. As a result, the OH bond weakens and ultimately breaks to split off a proton. This is responsible for the acidic nature of the carboxyl group. Carboxylate anion. After the removal of a proton, the resulting carboxylate anion is also stabilized by resonance as shown below. Thus, both carboxylic acid and the carboxylate anion are stabilized by resonance, but the resonance energy of carboxylate anion is more than that of undissociated carboxylic acid. This is due to the fact that the canonical structures 3 and 4 for the carboxylate anion are equivalent and also do not involve separation of positive and negative charges, whereas the contributing structures 1 and 2 for the undissociated acids are not equivalent and also involve separation of positive and negative charges. In other words, it is the greater stability of the carboxylate anion as compared to carboxylic acid which is responsible for the ionization and hence the acidic character of the carboxylic acids. Since the carboxylate anion is a resonance hybrid of two equivalent structures, therefore the negative charge is no longer localized on one or the other oxygen atom but is evenly distributed over both the oxygen atoms and the carbon atom of the carboxylate anion. As a result, each of the two oxygen atoms in the carboxylate anion is attached to the carbon atom by 1.5 bond as shown below. In other words, both the carbon-oxygen bond lengths in carboxylate anion must be equal and should lie in between CO and CO bond lengths. On the other hand, in carboxylic acid, the two carbon-oxygen bond lengths should be different, since one of the oxygen atoms is linked to the carbon atom by a double bond, whereas the other is linked by a single bond. The above conclusions are supported by X-ray and electron diffraction studies of the bond lengths of the carboxylic acids and their anions. For example, formic acid has two different carbon-oxygen bond lengths. CO bond length is 1.23 angstrom, whereas CO bond length is 1.36 angstrom. On the other hand, in formate anion, two carbon-oxygen bond lengths are equal, that is 1.27 angstrom, and lie in between the values of C double bond O bond length of 1.23 angstrom and CO bond length of 1.36 angstrom. Formic acid, sodium formate. Look at these structures. Comparison of acidic character of alcohols and carboxylic acids. Both alcohols and carboxylic acids contains an OH group, but carboxylic acids are much stronger acids than alcohols. For example, acetic acid is about 10 raised to power 10 to 10 raised to power 11 times a stronger acid than ethyl alcohol. This is due to the fact that both carboxylic acid and carboxylate anion are stabilized by resonance, but neither the alcohols nor their alkoxide ions are stabilized by resonance. On the contrary, alkoxide ion is destabilized since the alkyl group has electron releasing inductive effect, and this tends to intensify the negative charges on the oxygen atom. Stabilized by resonance. Look at these structures. Not stabilized. In other words, alkoxide ions are less stable than alcohols, and hence they have little or no tendency to release a proton. On the other hand, carboxylate anions are more stable than the carboxylic acids, and hence they have a stronger tendency to release a proton. This explains why alcohols are much weaker acids than carboxylic acids, who both contain one NOH group. Comparison of acidic character of phenols and carboxylic acids. Both carboxylic acids and phenols are acidic in nature, but carboxylic acids are stronger acids than phenols. To explain this, let us consider the resonating structures of the carboxylate ion and phenoxide ion. Here the resonance structures of carboxylate ion and phenoxide ion. Here's the comparison of these resonance structures. Look at these structures. In case of phenoxide ion, structures carry a negative charge on the less electronegative carbon atom. Therefore, their contribution towards the resonance stabilization of phenoxide ion is very small and hence can be easily rejected. Let us now consider only those structures which have a negative charge on the more electronegative oxygen atom, that is structures 1 and 2 for the carboxylate ion and the structures 3rd and 4th for the phenoxide ion in structures 1 and 2. The negative charge on the carboxylate ion is delocalized over 2 oxygen atoms, while in structures 3rd and 4th the negative charge on the oxygen atom remains localized, while the electrons of the benzene ring only are delocalized. Since delocalization of benzene electrons contributes little towards the stability of phenoxide ion, therefore the carboxylate ion is much more resonance stabilized than phenoxide ion. Thus, the release of a proton from carboxylic acids is much easier than from phenols. In other words, carboxylic acids are stronger acids than phenols. Effects of substituents of the acidity of carboxylic acid. Aliphatic acids. We have just discussed above that the acidity of a carboxylic acid is due to the powerful resonance stabilization of the carboxylate anion. Evidently, any factor which tends to increase the stabilization of the carboxylate anion over the carboxylic acid should increase the strength of the acid, and any factor which tends to make the anion less stable than the acid should decrease the acidity of the carboxylic acid. In the light of these arguments, it is expected that electron releasing groups such as alkyl groups would destabilize the carboxylate anion by intensifying its negative charge and hence should decrease the acidity. Conversely, electron withdrawing groups such as halogens etc. would stabilize the carboxylate anion. relative to the carboxylic acid by dispersing its negative charge, and hence should increase the acidity of the carboxylic acid. EDG donates electrons, destabilizes the anion, decreases the acid strength. EWG withdraws electrons, stabilizes the anion, increases the acid strength. Let us now discuss briefly the effect of various substituents on the acidity of carboxylic acids. Effect of electron donating substituents. If the non-hydroxylic acid hydrogen atom in formic acid is replaced by an alkyl group, the acidity of the carboxylic acid falls. For example, formic acid is about 10 times stronger than the acetic acid. This is due to the reason that the plus I effect of the methyl group destabilizes the acetate ion related to the formate ion by intensifying the negative charge on it. Further, since the plus I effect of the alkyl groups increases in the odor, the acidity decreases in the same order. Thus, acetic acid, propanoic acid, isobutyric acid, or pivallic acid. Effect of electron withdrawing substituents. Substitution of an alpha hydrogen of the alkyl group by an electron withdrawing group increases the acidity of an acid. For example, chloroacetic acid is a much stronger than acetic acid. This is due to the reason that the minus I effect of the chlorine atoms tends to stabilize the chloroacetate ion relative to acetate ion by dispersing the negative charge on it. Now, since the minus I effect of the halogens decreases in the order, the acidity of the alpha halo acids also decreases in the same order. Thus, further, greater the number of electron withdrawing substituents, greater would be the dispersal of the negative charge, and hence stronger will be the acid. For example, trichloroacetic acid, dichloroacetic acid, chloroacetic acid. We also know that the inductive effect decreases rapidly with distance. Thus, at the distance between the electronegative substituent group and the COOH group increases, the dispersal of the negative charge of the corresponding carboxylate ion becomes less pronounced, and hence the acidity decreases. For example, alpha chlorobutyric acid, beta chlorobutyric acid, gamma chlorobutyric acid. Aromatic acids. A COOH group has minus I effects as well as plus R effect as shown below. Plus R effect. Look at these structures. When phenyl group is directly attached to a COOH group, it has an overall electron donating effect, which is however weaker than the plus I effect of any alkyl group. As a result, unsubstituted aromatic carboxylic acids are stronger acids than unsubstituted aliphatic carboxylic acids. This benzoic acid is a stronger acid than acetic acid. Further, since formic acid does not contain any alkyl group, therefore it is a stronger acid than benzoic acid. Thus, the relative acid strength of formic acid, acetic acid, and benzoic acid follows the sequence formic acid, benzoic acid, acetic acid. However, when a phenyl group is attached to a carboxyl group through one or more saturated carbon atoms, phenyl group has a weak electron withdrawing inductive effect, minus I effect. Thus is attributed to the fact that sp2 hybridized carbon of the phenyl group in more electronegative than sp3 hybridized carbon atom of the aliphatic chain. It is because of this minus I effect of the phenyl group that phenyl acetic acid is a slightly stronger acid than acetic acid. Effects of the substituents on the acidity of aromatic acids. The nature and the position of the substituent on the benzene ring is a marked effect on the acidity of benzoic acid, as discussed below. List the pKa values of some important aromatic carboxylic acids. pKa values of some substituted benzoic acids. Look at in this table. From the above table, following points emerge. Electron donating substituents tend to decrease and electron attracting substituents tend to increase the acidity of substituted benzoic acids. The acid weakening effect of the electron donating groups and acid strengthening effect of the electron withdrawing substituents is more pronounced at p para than at meta positions. Ortho-substituted benzoic acids are usually stronger acids than benzoic acid regardless of the nature, electron donating or electron withdrawing of the substituent. This is called ortho effect and is probably due to a combination of steric and electronic factors. Explanation: the electron donating groups tend to destabilize the carboxylate ion relative to the undissociated acid by intensifying the negative charge on the carboxylate ion. As a result, these substituents decrease the acid strength of substituted benzoic acids relative to benzoic acid. Conversely, electron withdrawing substituents tend to stabilize the carboxylate ion relative to undissociated carboxylic acid by dispersing the negative charge on the carboxylate ion. As a result, such groups increase the acid strength of the substituted benzoic acid relative to benzoic acid. EDG donates electrons, destabilizes the carboxylate ion, decreases acidity. EWG, where withdraws electrons, stabilizes the carboxylate ion, increases acidity. Effect of the electron donating group at meta and para positions. The electron donating group decreases the acidity of acids. This decrease is more for the para than for the meta isomer. In other words, para isomers are weaker acids than meta isomers. This may be explained as follows. Resonance effect plus R effect releases electron, destabilizes the anion, decreases the acidity. At the same time, they have electron withdrawing inductive effect minus I effect due to higher electronegativity of the heteroatom than carbon as shown below. Inductive effect withdraws electrons, stabilizes the anion, increases the acidity. No resonance effect, only inductive effect minus I effect operates which stabilizes the anion, increases rapidly. These two effects operate in opposite directions, whereas plus R effect tends to decrease the acidity. The minus I effect tends to increase the acidity of the substituted benzoic acid. In the para isomer, both these effects operate, but in the meta isomer, only the minus I effect operates since the resonance effect cannot occur. Further, since the plus R effect overweighs the minus I effect, therefore para isomer are weaker acids than the corresponding meta isomer. For example, table 5.3, para hydroxybenzoic acid is a weaker acid than the meta hydroxybenzoic acid. Similarly, para methoxybenzoic acid is a weaker acid than meta methoxybenzoic acid. Effect of electron withdrawing groups at meta and para positions. Electron withdrawing groups increases the acidity of the acids. This increase in acidity is however greater at para than at meta positions. Para isomers are stronger acids than meta isomers. This may be explained as follows. All the electron withdrawing groups CN, NO2, COOR, etc. withdraw electrons both by resonance minus R effect and inductive effect minus I effect in para-isomers. Both these effects operate in the same direction and thus tend to increase the acidity of the acid. However, in meta-isomer, only the minus I effect occurs since minus R effect cannot take place. Therefore, para-isomers are stronger acids than meta-isomers. Resonance effect minus R effect withdraws electrons, stabilizes the carboxylate and ion, increases the acidity. Look at these structures. Inductive effect minus I effect withdraws electrons, substrate stabilizes the carboxylate ion, increase the acidity. And this structure, and in this structure, resonance effect cannot operate, only inductive effect minus I effect operates, which withdraws electrons, stabilizes the carboxylate ion, increases the acidity. Ortho effect. The ortho substituents have an acid strengthening effect, and this effect is unexpectedly large. Thus, ortho substituted benzoic acid are much stronger acids than their meta and para isomers, no matter whether the substituent is electron donating, example CH3, OCH3, OH, NH2, etc., or electron withdrawing, example Cl, NO2, Cn, COOR, etc. This effect is also called the ortho effect and is probably due to a combination of steric and electronic factors. In the light of above facts, the relative acid strength of ortho, meta, and paratoluic acids as compared to benzoic acids follows the sequence: orthotoluic acid, benzoic acid, metatoluic acid, paratoluic acid. Similarly, the relative strengths of ortho, meta, and para-hydroxybenzoic acids relative to benzoic acid follows the sequence: salicylic acid, meta-hydroxybenzoic acid, benzoic acid, para-hydroxybenzoic acid. Likewise, among nitrobenzoic acids, the relative acid strength follows the sequence: orthonitrobenzoic acid, para-nitrobenzoic acid, meta-nitrobenzoic acid, benzoic acid. Chemical properties. A molecule of carboxylic acids except formic acid is made up of two parts, that is, an alkyl or an aryl group and a carboxyl group. The carboxyl group may be further considered to be made up of a carbonyl group, as in aldehydes and ketones, and a hydroxyl group, as in alcohols and phenols. Therefore, carboxylic acids are expected to show the reactions of both these groups. However, the reactions expected of these groups are somewhat modified as a result of interaction between these groups due to their proximity. We have already discussed in SEC 5.2 that the carbonyl carbon in carboxyl group is less electrophilic than the carbonyl carbon in aldehydes and ketones due to resonance. Therefore, many nucleophilic addition reactions such as formation of oximes, hydrazones, phenylhydrazones, 2,4-dinitrophenylhydrazones, and semi-carbozones of aldehydes and ketones do to take place with carboxylic acids. From the above discussion, it follows that the reactions of carboxylic acids are characteristics of the carboxyl group and the alkyl or the aryl group, and are studied under the following headings: reactions due to H atom of the carboxyl group. A few reactions showing the acidic character of the carboxylic acids are given below. Reaction with petals: carboxylic acids react with the active metals like Na, K, Ca, Mg, Zn, etc. form their respective salts, liberating H2 gas. Example: acetic acid to sodium acetate, acetic acid to zinc acetate. Reaction with carbonates and bicarbonates: carboxylic acids decompose carbonates and bicarbonates, producing CO2 gas, acetic acid to sodium acetate. This reaction is used to detect the presence of a carboxyl group in an organic compound. Since most of the phenols do not produce Everafins with aqueous solution of NaHCO3. Therefore, this reaction can also be used to distinguish phenols from carboxylic acids. Reactions with alkalis, carboxylic acids react with hydroxides and metallic oxides to form salts. Sodium carboxylate, ammonium carboxylate. It may, however, be noted that carboxylic acids are much weaker acids than mineral acids like HCl, H2SO4, and HNO3. Therefore, salts of carboxylic acids are readily decomposed by these mineral acids to regenerate carboxylic acids. Reactions involving the OH group of carboxylic acids, formation of functional derivatives, the hydroxyl group of a carboxylic acid. Like the hydroxyl group in an alcohol can be replaced by a number of groups such as Cl, OR NH2 and OOCr to form acid chlorides, esters, amides and anhydrides respectively. These derivatives are collectively called as functional derivatives of carboxylic acids. Formation of acid chlorides, reactions with SOCl2 PCl5 or PCl3 carboxylic acids react with the thionyl chloride, phosphorus pentachloride or phosphorus trichloride to form acid chlorides by replacement of the OH group by Cl atom. Thionyl chloride, acid chloride. In actual practice, thionyl chloride method is prepared to PCl5 or PCl3 method since both the byproduct SO2 and HCl being gases escape into the atmosphere and the thionyl chloride being volatile can be easily removed by fractional distillation leaving acid chlorides in almost pure state. Butyric acid plus thionyl chloride, butyryl chloride. Formation of esters, reactions with alcohols when carboxylic acids are heated with alcohols in presence of concentrated H2SO4 or dry HCl. Fischer-Spear esterification. Esters are formed. The reaction is reversible in nature and is known as esterification. Carboxylic acid plus alcohol to ester, acetic acid plus ethyl alcohol to ethyl acetate. Since esterification is an equilibrium reaction, therefore to shift the equilibrium in the forward direction, either the carboxylic acid or the alcohol is used in excess. It is usually the alcohol which is taken in excess. The yield of the equilibrium reaction can be further increased by removing water from the reaction mixture as it is formed by using a special apparatus called Dehn-Stark apparatus. Mechanism of esterification has already been discussed in Unit 1. Relative reactivities of acids and alcohols. The rate of esterification is sensitive to steric hindrance. As the number and size of the subsequents around the COOH group or the OH group in alcohols increases, the rate of esterification slows down. Thus, the order of reactivity follows the sequence. Look at this sequence: acids, alcohols, primary, secondary, tertiary. Look at this. Formation of amides. Reaction with NH3 when treated with ammonia, carboxylic acids from ammonium salts which upon heating lose a molecule of water to form acid amides. Ammonium salt to acidamide, benzoic acid, ammonium benzoate, benzamide. Formation of anhydrides. Action of heat in presence of P2O when carboxylic acids are heated in presence of a strong dehydrating agent such as phosphorus pentoxide acid. Anhydrides are obtained by the elimination of a molecule of water from two molecules of the acid. Carboxylic acid, two molecules, acid anhydride. Acid anhydrides can also be obtained by treating acid chlorides with carboxylic acids in presence of pyridine or as a base or by treating acid chlorides with sodium salts of carboxylic acids. Carboxylic acid plus acid chloride to acid anhydride. Acetic acid plus acetyl chloride to acetic anhydride. Reactions involving the carboxyl group as a whole. Carboxylic acids and their salts undergo a number of reactions which involve either the elimination or the decomposition of the carboxyl group. Some of these reactions are discussed below. Decomposition or decarboxylation. Chemical decarboxylation. Sodium salts of decarboxylation acids, when distilled with soda lime NaOH plus CaO, undergo decarboxylation to yield alkanes. Alkane. Sodium benzoate, benzene. Mechanism. Decarboxylation occurs through intermediate formation of a carbanion which subsequently picks up a proton to form the corresponding hydrocarbon. Look at below. Carbanion, hydrocarbon. Effects of substituents on decarboxylation. Since formation of carbanion or organosodium compound is the key step in the above reaction, therefore any factor which tends to increase the stability of the carbanion should increase the rate of decarboxylation. Thus, carboxylic acids which contain an electron withdrawing group such as NO2, COOH, COCH3, etc. at beta position, the COOH group readily undergo decarboxylation on heating through a 6-membered cycling transition state. For example, beta keto acid, 6-membered cyclic transition state, acetone. Similarly, Chem decarboxylic acids, that is compounds in which the two carboxyl groups are attached to the same carbon atom, readily undergo decarboxylation on heating. Malanoic acid, acetic acid. Electrolytic decarboxylation, electrolysis of aqueous solutions of sodium or potassium salts of acids gives alkanes. This process is called Kolb's electrolytic reaction. At anode, at cathode. At anode, unstable alkane. At anode, both Na positive and H positive from H2O are present, but H positive ions are preferentially discharged due to the lower discharge potential. Na positive ions and thus hydrogen gases evolved at the cathode. The overall Kolb's reaction may be represented as sodium carboxylate alkane. Electrolysis of sodium formate, however, yields to only H2 but not an alkane. Decarboxylation of silver salts of carboxylic acids in presence of bromine. The silver salts of carboxylic acids on treatment with Br2 in refluxing CCl4 gives alkyl aryl bromides containing one carbon atom less than the parent acid. For example, silver acetate, methyl bromide, silver benzoate, bromobenzene. This reaction is called Hunt's-Dicker reaction. Mechanism. The reaction occurs by free radical mechanism through intermediate formation of acyl hypobromite as shown below. Acyl hypobromite, acyl oxy radical, alkyl halide, alkyl bromide plus S-cycloxy radical. Decomposition of calcium salts of fatty acids. Dry distillation of calcium salts of fatty acids gives aldehydes or ketones. For example, dry distillation of calcium formate gives formaldehyde, calcium formate to formaldehyde. Dry distillation of calcium salt of an acid other than that of formic acid gives a ketone. Calcium carboxylate ketone. Dry distillation of a mixture of calcium formate and calcium salt of any acid other than formic acid gives an aldehyde other than formaldehyde. Reduction to alkanes. Carboxylic acids on reduction with hydriodic acid and red phosphorus at 473 Kelvin gives alkanes. Alkane, acetic acid, ethane. In the above reactions, the COOH as a whole is reduced to a CH3 group. Reduction to alcohols. Carboxylic acids are resistant to catalytic hydrogenation. However, reduction of carboxylic acids with lithium aluminium hydride LiAiH4 or better with dibromine B2H6 gives primary alcohols. During this reduction, CO group of the carboxyl group is reduced to CH2. Thus, RCOOH to primary alcohol, uric acid to uryl alcohol. This method is used for preparation of alcohols from acids which are readily available from natural sources. The reduction of carboxylic acids can also be brought about by first converting them to esters, which are then easily reduced to alcohols by sodium and alcohol Wavelength blank reduction, carboxylic acid ester. Reactions of the alkyl group halogenation, carboxylic acids expect formic acid which does not contain an alkyl group react with chlorine or bromine in presence of small quantities of red phosphorus to give exclusively alpha chloro or alpha bromic acids. This reaction is called Helmholtz-Zielinski HVZ reaction. If more than one molecule of chlorine or bromine is used, the second and the third alpha hydrogen atoms can be successively replaced. For example, acetic acid, chloroacetic acid, dichloroacetic acid, trichloroacetic acid, propanoic acid, alpha bromopropanoic acid, alpha alpha dibromopropanoic acid. It may be noted that bromination exclusively occurs at the alpha position, and the reaction stops after all the alpha hydrogens have been replaced by the bromine atoms. In contrast, chlorination first occurs at the alpha position, and when all the alpha hydrogens have been displaced, it occurs further along the chain. Function of red phosphorus. Red P first combines with Br2 to form little PBr3. This then reacts with carboxylic acids to form the corresponding acid bromide, which analyzes to a great extent then the acid and thus bring about alpha bromination easily. Propanoic acid, propanoyl bromide enol from 2-bromopropanoyl bromide. Reduction properties of formic acid. Formic acid is a unique among a simple carboxylic acid since it contains a hydrogen acid atom instead of an alkyl group. Thus, formic acid may be regarded both as an aldehyde as well as carboxylic acid like aldehydes. It can be easily oxidized to carbonic acid, which decomposes to give CO2 and H2O, carbonic acid. Thus, like aldehydes, it acts as a reducing agent. As such, it reduces Fehling solution to red PPT of CO2. Tollens reagent to silver mirror, dichlorizes acidified KMnO4 and K2Cr2O7 solutions. Formic acid also reduces mercuric salts to mercurous salts, white PPT. However, unlike aldehydes, formic acid does not form an oxime, a phenyl hydrazone or semicarbazone.